Well, the rules we've been using so far have told us that if we're interested in finding the limit as x tends to infinity or negative infinity of a fractional expression, those rules apply if n is greater than 0, and we might reasonably ask, well, what if n is not a nice whole number exponent? What if it's not an integer exponent? What if it's a fractional exponent? Would the rule still work? And the answer is, well, yeah, most definitely it would. And here's the way this would work. If I were to take my limit as x tends to infinity, let's say, of 5 times x to the 3/2 power, which is a nice fractional exponent, divided by 4x squared plus 1, I'm going to use exactly the same rule that I did before, which is to multiply by 1 over x to the highest power in the denominator. So 1 over x squared. Okay. Now we have to be clever and remember our rules for dealing with exponents in division. In division, if we were to take x to the 3/2 divided by x squared, right, let's go back. If I were to take x to the 3/2 divided by x squared, our rule was that this would be the same thing as x to the uh, 3/2 minus 2, which we know to be x to the negative 1/2. But because it's a negative exponent, it's the same thing as 1 over x to the 1/2 power. Don't forget, we're subtracting these exponents, and when we subtract the negatives in the exponents and make that expression go to the denominator. So in our case, we've actually got 5 over x to the 1/2 power. And that's going to be divided by 4x squared over 1x squared, which is just 4, plus 1 times 1 over x squared, that's just 1 over x squared. And so now we look at what happens to each of these terms. In the numerator, it doesn't matter that it's x to the 1/2, because as x gets large, eventually 5 over x to the 1/2 goes to 0. As long as that n is greater than 0, that's the case, right? And x to the 1/2, that's true. And we've divided it by 4 plus 1 over x squared, which also goes to 0. And so the entire limit itself goes to 0. And that's it. All right, let's try another one. This time, we've got a limit where the numerator has a greater power than the denominator. Now, if you recall, if we're using our horizontal asymptote rules from algebra, we might say, well, that means there is no horizontal asymptote. Well, that's true. But we want to decide what the behavior of this function is. So one way of doing that is to carry out long, or synthetic division if appropriate, right here. And I'm going to carry out a long division just to show how this works, but you can use synthetic division as well. Because the degree of the numerator is greater than the degree of the denominator, the very first thing you should do is simplify that by either doing long division or, if appropriate, synthetic division. This is x minus 2 being divided into x cubed plus, and we have to put in our placeholder, 0x squared minus 2x plus 1. All right, let's carry out that division. How many times does x go into x cubed? The answer is x squared, right? X squared times x would give us x cubed, which is what we would plan, minus 2 times x squared. And so we subtract that away, and we're going to get 0 plus 2x squared here. And so we'll bring down the next term, minus 2x. And we say, what would you have to multiply by x to get 2x squared? Answer, plus 2x. So 2x times x gives us 2x squared as planned. And 2x times negative 2 gives us minus 4x. And we subtract that quantity away from the quantity above. That's going to be 0, negative 2 plus 4x, that's 2x plus 1. And now we might ask, well, what could I multiply by x to give me 2x? Answer, plus 2. 2 times x is 2x, and 2 times negative 2 is negative 4. And remember, I'm subtracting that away from the line above it, and that gives me 5. X minus 2 is no longer divisible into 5, so that's our remainder. And recalling the way that it worked in algebra, this means that our rational expression x cubed minus 2x plus 1 over x minus 2 is equivalent to the expression x squared plus 2x plus 2 plus the remainder of 5 over x minus 2. Now we might recognize exactly what's going to happen to this term as we let x go to infinity. This term is going to go to 0. You might ask why. Well, it's 5 over x, or 5 over x minus 2, and you know exactly what's going to happen. That term's going to go to 0. So we ask about what about the rest of it? Well, in this case, we've got x being raised to an even power as our highest term. When that's the case, it doesn't matter that it's going to negative infinity. Our rule stated that as long as x is going to a power, an even power right here, that highest power dictates the direction for the rest of this polynomial part of the expression. And so it's like saying positive infinity plus 0, which is from this last term, and so the result is positive infinity. That's our limit in this case. This term, this expression, tends towards positive infinity as x goes to the left. Okay, more to come.